Hello learners and welcome back to VLSI Simplified. So this is part 2 of our abstraction levels in Verilog series. And if you haven't watched part 1 yet, I highly recommend checking that out first. So in that video, we started from the very basic, exploring switch level and gate level modeling and how Verilog lets us describe circuit using transistor and logic gates. You will find a link in the description or right here on the screen. Go give it a watch and then jump back here. So now in the part 2, we are stepping up the abstraction level and exploring the level. We will talk about behavioral modeling and RTL, and you will see how Verilog gets more elegant and readable. And just like before, we will stick to our trusty ungate example to keep things simple and consistent across levels. So let's dive in and see how Verilog becomes more designer friendly as we move up. Here's what you are going to take away from this video. You will understand how behavioral modeling allows us to describe circuit behavior using high-level constructs like if, case, and loops. Then we will move into RTL modeling, which is what most real-world Verilog designs are based on because it's synthesizable and reflects how data moves in actual hardware. We will compare both behavioral and RTL side by side and will show you when to use what. Alright, this is VLSI Simplified. Let's get started and let's simplify.
Feel me like a Hellcat.
Now, let's talk about behavioral level. This is where things start to feel a lot more like writing a logic in a programming language. At the behavioral level, you are describing what the circuit should do and not how it's built underneath. So you are not talking about gates or transistors anymore, you are just expressing the logic or the behavior. So Verilog gives us a rich set of high-level constructs like if, case, for, and while, along with blocks like always and initial. So using this, you can quickly describe complex decision making, control flows, or functional logics. So this level is widely used in simulation and test benches because it's easy to model and test behavior without worrying about synthesizability at all the time. However, not all behavioral codes are synthesizable. So some constructs like delays or forever loops are simulation only. But if you write your behavioral logic properly, as you will see in the next slide, it can be synthesized into real hardware. Now let's take a look at how to model a simple AND gate using a behavioral approach. So now let's see how we can describe an AND gate using behavioral modeling in Verilog. So here, instead of specifying gates or logic primitives, we are focusing on what the output should be when input A and B changes. So we use an always block with the sensitivity list at A or B. So this means the logic inside gets evaluated whenever A or B changes. So inside the block, use a simple if statement. So if both A and B are high, Y is assigned to 1, otherwise Y is 0. So this style is very readable and easy to extend for more complex logics. Also, the good news is this code is synthesizable because we written in a structure that the synthesis tool can understand. So behavioral modeling helps you to express intent and it's widely used in both design and verification. But when we want to actually implement designs of hardware, we take it one step further to RTL modeling. So let's explore that next. Now let's talk about RTL, register transfer level. So which is the most important abstraction level for real world digital design. And here is a key idea to remember. That is, RTL is nothing but a code that can be synthesized into actual hardware. That means everything you write in at this level should follow a synthesizable coding practice. So at this level, we are not just describing behavior anymore. We are defining how data moves between registers and usually synchronized with the clock. So this is where Verilog becomes hardware focused because you are writing a code that directly maps to flip-flops, multiplexers or other combinational logics in silicon. So RTL is used in almost every real ASIC or FPGA design, and it's how processors, state machines and data paths are actually built. You define what happens on the rising edge of a clock, how reset behaves, and how values are passed across logic. And the best part, RTL Verilog is fully synthesizable. So meaning it can be taken from your code, passed through a synthesis tool and turned into a gate level hardware that can actually be fabricated. So this is the level you will spend most of your time in as a front-end VLSI design engineer. Now, let's look at how we can write an AND gate at the RTL level. Here is how an AND gate looks at the RTL level in Verilog. Notice the addition of a clock input. We now define the logic inside the always at passage of clock block. So which means this block only executes on the rising edge of a clock. So inside the clock, we use the non-blocking assignment that is less than equal to. This is the correct way to model sequential logic in Verilog. So it ensures the logic behaves properly in the simulation and synthesis. This means we are no longer just saying if A and B are 1, output Y should be 1. Instead, we are saying on the next clock edge, assign the AND of A and B to the output Y. This is exactly the kind of logic that gets synthesized into flip-flop and the combinational gates during RTL synthesis. It is simple, structured and hardware ready. That's what makes RTL modeling so important. Let's break down the key difference between behavioral and RTL modeling. First, both use similar constructs like always, if, case and even loops. So, if we have written behavioral Verilog, RTL might look familiar. But here's the catch. The indent and the structure change everything. So in the behavioral modeling, we are describing what the circuit should do, often without worrying about the timing. It's great for writing test benches or simulating logic in the high level way. Clock signals may or may not be involved. In RTL modeling, we will still use always, if and case. But we will use inside the always at passage of clock. So this introduces timing and clock awareness. So you are now describing how data flows between registers on every clock edge. And that's what makes it ready for synthesis. So yes, both uses the same keywords. But how you apply them and whether you structure your logic around the clock decides if your code is RTL or not. Let's now take a step back and look at how all these abstraction levels compare side by side. Now, let's take a moment to compare all the abstraction levels just we covered and really get a sense of how they stack up against each other. So at the behavioral level, it's all about high level functionality. So you are writing what the design should do without worrying about how it is implemented in hardware. It's like sketching out the idea for a project. This is great for early design stages or creating test bench, and you are typically not concerned with timing or a clock. When we move to RTL level, things starts to get more concrete. This is where the magic happens if you are looking to actually synthesize your design into hardware. You are still using those familiar constructs like always, if and case. But now everything happens on the clock edge. It's all about how data flows between registers and what happens on the each clock cycle. So you are moving from the abstract functionality to something that can be synthesized into actual gates and flip-flops. Next, the gate level abstraction comes into play when we are already synthesized the design or want to look at how it implements at the gate level. This is where the design is broken down into individual gates like and or not. And you start seeing how your logic gets translated into actual hardware components. This level gives you a deeper and more detailed view of how the design is going to behave on a physical chip. And finally, switch level. The switch level takes us to the lowest level of abstraction, the transistor level modeling. Here, we are talking about the details of how transistors, resistors, and capacitors behave. So this level is used for deep physical analysis where we consider things like parasitic delays, other real-world phenomena that might affect the performance. So it's not something you will deal with every day, but when you need that level of precision, this is where you go. So when you compare these levels, you can see they progress from high-level behavior to the low-level detailed hardware design. So every abstraction level has its purpose. And as we move down the chain, they get closer and closer to actual hardware. But for now, let's pause and take a look at how they compare side by side in this table. Alright, before we go further, let's address a common and important question. Does RTL always mean everything is clocked? The short answer is no, not everything is clocked. In fact, combinational logic is a crucial part of RTL design. It is used to process input and drive outputs between clocked registers. But when we talk about RTL in the VLSI industry, we focus on how data moves through registers, which are triggered by clock edges. So, while combinational logic doesn't require a clock signal, it still lives inside a clock-driven system. That's why RTL is considered clock-centric even though it includes both sequential and combinational elements. This distinction is important to understand before we jumping into synthesis. Let's make this more relatable with a simple analogy, making a sandwich. So the behavioral level is like telling someone to make a sandwich. You don't tell them how to do it, just you are telling the desired outcome. In RTL, you give them a step-by-step recipe. You specify the steps involved, what goes where and in what order. But you are not giving the exact tools or brands. So this mirrors how RTL defines what data flows where and when. So at the gate level, you take control of exact implementation. You are specifying what exact kitchen tools to use, much like how gate level code specify which exact logic gates will perform operations. So this analogy helps grasping the increasing level of detail and control as we move down the abstraction ladder. Alright, that brings us to the end of part 2 in our abstraction level series. We learned what behavioral and RTL levels really mean, how they differ, and how an AND gate looks in both styles. We also cleared up the confusion that RTL doesn't always mean clock based design and that includes combinational logic too. Now that you know what kind of code represent each level. So in the next video, we'll dive into building blocks of Verilog, starting from modules, ports, and how to structure your first Verilog design. So stay tuned, it's about to get really exciting. Subscribe to our channel so you don't miss our upcoming videos. See you in the next video. Bye.